Hi folks, this is Checkpoint Quiz 4.2. We're asked to use the 6-step procedure discussed in class to graph this rational function. Now once again, on a test, I'll have the 6 steps spelled out for you. But just to save room here, I will just remind you of them as we go along. So the first step in analyzing a rational function is to find the domain. A rational function, we have to worry about the denominator being 0. So we're going to set the denominator equal to 0 and figure out what the bad guys are. So we can factor an x out of both terms. I'm left with x squared minus 4. And I can break this down using difference of squares. Now that I've factored it, I set each factor equal to 0. So x is 0 here. X minus 2 equals 0 would give us x is 2. X plus 2 equals 0 would give us x is negative 2. So for my domain, x can't be 0, 2, or negative 2. So in interval notation, it's everything up to negative 2, along with everything between negative 2 and 0, along with everything between 0 and 2, along with everything bigger than 2. We want to keep the domain in mind through each step of the process. Alright, so that'll do it then for step 1. Okay, in step 2 we need to reduce the function to lowest terms. And so I've got my function r of x, and just like any fraction, the way we're going to reduce it to lowest terms is we're going to factor the numerator and denominator and cancel out what's in common. Okay, so we get started here. The denominator we already factored from when we did the domain. So I've got that. And now in the numerator I can get started by factoring out an x. And I'm left with 2x squared minus x minus 3. I can further break this down. So I need factors of 3 I can combine with the 2 to give me a minus 1. So I can do an x plus 1 here, and x minus 3 here. And I can check minus 3x plus 2x gives me minus x, so we're good to go. And I look to see what cancels out here. And the x's cancel, and that's it. So the reduced form of my function is going to be this over this. So then I'll go ahead and multiply that back out. 2x squared minus x minus 3 over x squared minus 4. So this is the reduced form of my function. And so this is the form that I'll use through the rest of the analysis. Alright, here's the reduced formula for our function. Our next step is to find the intercepts. The intercepts of the graph, they come in 2 varieties. First variety is the y-intercept. So for the y-intercept, we set x equal to 0 and plug that into the function. And this is where you have to be really careful. If you plug x equals 0 into this function, in the numerator you'll get negative 3, and the denominator you'll get negative 4. And so you may be tempted to say, oh, okay, we have a y-intercept of 0, 3/4. But you'd be incorrect. Why? The domain. Okay, x equals 0 is not in the domain, so we're technically not allowed to plug 0 into it. We're going to end up having a hole in the graph at x equals 0. We'll see that in the next step. So to find the y-intercept at x equal to 0, there is no y-intercept, because x equals 0 is not in the domain. So let's move on to see if we have any x-intercepts. To get the x-intercepts, we set the y on the graph equal to 0, but the y is the actual function. So we're setting that equal to 0. And the first thing we'll do is multiply both sides by the denominator. it cancels out over here and it zeroes out over there, and that's going to give us this guy is 0. So the factoring we did in step 2 isn't all wasted because we know exactly how this guy's going to factor. And we set each factor equal to 0. If I set 2x minus 3 equal to 0, I get x is 3 halves. If I set x plus 1 equals 0, I get x equals negative 1. And I just do a quick double check. Both of these numbers are in the domain, so I actually get 2 x-intercepts. And remember, x-intercepts are points. We get 3 halves 0 along with negative 1 0. So that'll do it for step 3. Okay, now for step 4, well, we need to analyze what's going on near the values excluded from the domain and determine if we get vertical asymptotes or holes in the graph. And so if I look at my reduced function, we can use a theorem from section 4.1 to tell us where we're going to get vertical asymptotes and holes, depending on where or what happens when I plug in the values excluded from the domain. If I plug in x equals 0 into this, I get negative 3 on the top, and I get negative 4 on the bottom. Since I'm no longer getting a 0 on the bottom, I know that I have a hole in the graph at 0, comma, plug 0 in 3/4. When I substitute in x equals 2, I'm going to get a 0 in the denominator still, which means there's a vertical asymptote. X equals 2 is a vertical asymptote. And likewise, when I plug negative 2 into this, I get a 0 in the denominator, so I get a vertical asymptote as well at x equals negative 2. Okay, so that's just using the theorem from section 4.1. But we could do a detailed analysis, and it's worth going through because it helps build number sense that you'll need if you're going into calculus. So let's look near x equals 0. And there's two ways we can get close to 0. We can get close to 0 coming from the left or coming from the right. So let's look as x approaches 0 from the left-hand side. So we're looking at 0 minus a little bit. So numbers like negative 0.1, negative 0.01, etc. Okay? And let's sample the function at, say, at negative 0.01. I would substitute in negative 0.01 squared minus negative 0.01 minus 3 divided by negative 0.01 squared minus 4. Now, as x gets closer and closer, 0 from the left, what's going to happen to these terms in the numerator? Well, this is getting close to 0, so 2 times it is getting close to 0. And this is getting close to 0. And so the numerator is getting close to negative 3. This is getting close to 0. 0 squared minus 4 is pretty close to negative 4. So that's 3/4. If I come into 0 from the right-hand side and plug in numbers a little bit bigger than 0, so 0.01 say, and I plug that into my function, the smaller the number I plug in here, the closer these terms will be to 0. So the numerator still is pretty much negative 3. The denominator is still pretty much negative 4, 3/4. And so together this tells me that I've got a hole at 0, 3/4. Okay, so the theorem from 4.1, the reason why we get a hole in the graph is because as we get close to x equals 0, the function values on the graph, the y values on the graph, get close to 3/4. So this would be considered a detailed analysis of what's going on near 0 to explain why we're getting a hole there.